Welcome everyone. It's a great pleasure to host Shachar Lovett from UCSD, who is giving the series of Erdős lectures this year. So the first one is today, and then there are two more talks. One is during the combinatoric seminar on Monday, and one is during the CS theory seminar on Wednesday. So thank you very much. And the title of the talk is Tensor ranks in their application.
Thanks, Tammy. Thanks, everybody. So now I was thinking, what do I want to talk about in these sort of Erdős lectures or talks? And I thought that one thing I wanted to tell you about is about sort of structure and how different types of structure play a part in questions that we think about in theoretical CS and in combinatorics and in other sort of adjacent mathematical areas. And today I want to tell you about some aspect that comes out in understand algebraic structure and specifically tensor ranks. And then, like Tammy said, there are two more talks. So the one on Monday is going to be in the combinatoric seminar, and then I'll talk about combinatorial structure, in particular how it plays a part in some questions in Boolean function analysis. And one on Wednesday, the theory seminar, is going to be about geometric structure and how, again, this plays a part in questions that come in theoretical machine learning and in discrete geometry. So what's my goal for this talk? So that's going to be sort of like a survey talk about this area of tensors and tensor ranks. And in particular, I want to show you how when you try to generalize the notion of rank from matrices to higher dimensional objects, there's more than one way to do it, and sort of, different notions of rank come up naturally in different applications, and sort of lead into different types of questions. And in particular, we'll see that a lot of the tensors that come up naturally in applications are not some arbitrary tensors, but you start from some base tensor, and you take a high tensor power of it. And so again, that's basically what I want to focus on about today, and there'll be a lot of open problems that people are interested in to think about. So tensors. So by the way, when PowerPoint suggested that automatically a background for tensors, it's just this background. I'm not sure why, but I guess there's some connections there. So what are tensors? So tensors are sort of higher dimensional analogs of matrices. And I'll call the K-tensor to be a K-dimensional tensor. So think like a 3-dimensional or 4-dimensional object. And for the most part, unless I have to, I'll stick with K equal to 3 because it's just one next step beyond 2 dimensions, and it's easier to draw. So this is like an example of a 3-dimensional tensor. So how can we understand tensors? So again, let's fix some field. F could be finite field or the reals or the complexes. And I'm going to work with a 3-dimensional tensor that's going to be of size n by n by n. You can have different sizes, but why complicate things? And there are two equivalent ways that you can view a tensor. And for some applications, one is more natural than other. So one is a combinatorial viewpoint where you just take a 3-dimensional array, and it has entries, like the 3 x's, I, j, k, like the x, y, and z coordinates, and just write the entries, like the entries of a matrix, but in 3 dimensions. And the other way that's also very useful is as a polynomial, as a multilinear polynomial, where we sort of think of the tensor as acting on 3 vectors, x, y, and z, where they're in f to the n, they're n-dimensional vectors. And the polynomial, the multilinear polynomial, is just the natural polynomial. You get by multiplied on x, on one axis and y and z, on the other 2 axes. So I want to show you 2 different examples of how tensors come up in applications. And in one of them, the algebraic one will be more natural, and for other one, the combinatorial one. But it's good to always have both of them in your mind when you're thinking about tensors. So the first example is what's called the matrix multiplication tensor. So we're trying to understand how fast can we multiply matrices. So it's a computational problem. And so we have, let's say, and for some reason that I'll explain a bit, it's actually easier to talk about 3 matrices, not 2 matrices. So take 3 matrices, A, B, and C, to be M by M matrices. And the tensor multiplication tensor is a tensor whose dimensions are M squared. And because each matrix has M squared entries. And then if you view it as a multilinear polynomial, so you think of your input as being the 3 matrices, then what you compute is you take the product and compute the trace. So it's a multilinear polynomial. And if you're trying to understand what the coefficients of these polynomials and get this sort of combinatorial viewpoint, then you get the following equation. So it's natural to index each one of the 3 inputs by the entries of the matrices. So I1, J1 will be like the entries of A, and similarly for B and C. That's going to be my polynomial. And the entry is going to be either 1 or 0, depending on the 1 if if these 2 indices match and they match and those 2 match, and otherwise it's 0. So it's just matrix multiplication. Okay, so why do we care about this tensor? We care about it because it turns out that it captures the computational problem of multiplying 2 matrices. And concretely, and I'll show you this more a bit later, the matrix multiplication tensor, really there's a notion of rank of tensor. That's going to be the first notion of rank we're going to explore. And the rank of this tensor turns out to exactly capture the computational problem of how hard it is to multiply 2 matrices. So that's going to be the first notion of rank. And again, I'll define this notion in a few minutes, but this is going to be our first notion of rank, maybe the simplest one. So here's another example. This is one coming from combinatorics. So this is called the capset tensor. So let me start by defining the tensor, then tell you why we care about it. So it's going to be, so choose some integer d. And the capset tensor is going to be of dimension 3 to the d by 3 to the d by 3 to the d. And this one is actually more natural to define combinatorially. So let's identify the 3 indices, Instead of being numbers, 1 up to 3 to the d, just think of them as entries of f3 to the d, just a way of indexing them. And then the ijk entry of this tensor is going to be 1 or 0. It's 1 if they sum to 0, as vectors in f3 to the d, and it's 0 otherwise. Okay? So in this case, this combinatorial viewpoint is easier. And if you want to write this as a polynomial, then you get the following polynomial, right? And again, why do we care about this tensor? So it turns out that this tensor exactly captures a Ramsey-type question in combinatorics. What is this question? So we're in f3 to the d. So a line here in f3 to the d is just 3 points, distinct points, I, j, k, that sum to 0. So you can verify that this is if and only if it's a line. And for some reason that I don't know, a subset of f3 to the d that doesn't contain a line is called the capset. Okay? That's a name for it. And the question is, how large can such a capset be? Okay? And turns out that understanding this, or the best ways we know to do it, is using another notion of rank called slice rank, but for this tensor. So that's going to be 2 different sort of examples that I'm going to go back to as we sort of explore different notions of rank. So let's start with the first one, tensor rank. By the way, it should be obvious, but if anybody has any question, then please stop me and ask. So what is tensor rank? So what's the most natural way of defining a rank of an object? You can say, well, the rank of a tensor is the minimal number R that I can decompose my tensor T as the sum of atoms. What are the atoms here? They are rank 1 tensors. Well, so now this sort of reduces the question of rank to what are rank 1 tensors. So what is a rank 1 tensor? So we said tensor with rank 1, we view it as a polynomial. It's a multilinear polynomial is rank 1 if it factors as a product of linear functions in each one of the 3 variables, x, y, and z. Or if you want to view this combinatorially, tensor is rank 1 if I can write its coefficients, ti, j, k, as a product of some vector ai times bj times ck. Okay, so that's a very natural object of a rank 1 tensor. And one thing to notice, and this is going to come up later, this notion of rank is sub-additive, right? If I give you 2 tensors, t and t prime, and I add them up, the rank that most grows as a sum. And the reason is simple, because if T is the sum of, I don't know, 10 rank 1 tensors, this is the sum of 20 rank 1 tensors, then summing them up, I get 30 rank 1 tensors. And again, there might be more efficient ways to do it, but at least you can do it in this way. Okay? So I'll say natural notions of rank that come up as summing basic objects are always going to be subadditive. That's just a useful observation. So what's the connection between tensor rank and matrix multiplication? So let me explain the connection. So reminding you that this matrix multiplication tensor corresponding to multiplying m by m matrices is an m squared by m squared by m squared tensor, defined in this way as a trace of ABC. And a remarkable result of Strassen from the 70s is that the rank of this tensor essentially captures the complexity, the computational complexity of multiplying two m by m matrices. So what's the connection? So before the connection, so what do we know about this problem? So typically people denote the rank of this as m to some constant omega. And omega is known as a matrix multiplication tensor. It's trivially between 2 and 3. It's at least 2 because that's the dimension. A has m squared entries, and 3 corresponds to like the very naive multiplication. And starting from Strassen, and there will be a long sequence of works improving this exponent. And I think in the last maybe 10 years or so, there's been also a sequence improving like the fifths and the sixth digits of this exponent. And I believe that's the latest work in the sequence. This improved over the previous one by like the 6th digit or something like that. And there have been sort of sequence of works, but also we know that all these approaches are going to get stuck at some number more than 2. And I mean, I won't talk about this today, but these techniques of slice rank, these notions of tensor ranks, are also ways of proving barriers on the current best techniques of designing these type of algorithms. So I mean, I will not discuss this now, but just be aware that this connection also exists. So why is this connection? So let's think about some way of writing, this tensor as a rank R. So it's going to be the sum over R rank 1 tensor. So what is Fi? Fi is some linear function in the entries of the matrix A, and similar Gi and Hi. So how can I use this to multiply the matrices, or to compute, let's say, the trace of ABC? Well, if I could compute this Fi, Gi, and Hi for free, if additions were free, I would only need to multiply R things, or 2 R things. But of course, if you do it naively, then the number of additions you need is much bigger, because each one has like m squared entries, and I have like maybe 3 R of those, so like 3 m squared R. But the main observation is that you don't have to plug in values here, coefficients, numbers. You can put in matrices as entries of the matrix ABC, and matrix multiplication has this very nice structure that if you take matrices of matrices and you multiply them, it's the same as multiplying just larger matrices. So what Strassen showed using this observation is that the number of additions here, using recursion, can be reduced from this larger number to really the optimal number of linear in the number of entries, order of m squared. So really all that you care about when you're trying to multiply large matrices is how many multiplications you make. And this is like just order of R. And really what this encapsulates, and I'll show you this in the next slide, is that matrix multiplication for large matrices is not some weird tensor. It comes from like high tensor powers of very simple tensors. Let's say, for example, 2 by 2 matrix multiplication. And this is what underlies everything here. And this again, another result here by Bauer and Strassen showed that if you can compute such a, let's say, polynomial in some amount of time, then you can compute all its first order derivatives in essentially the same amount of time. And if you compute the first order derivatives with respect to C, you exactly get the product of A and B. Okay. So and this is how the things get connected. This is at the high level. So what is this high tensor power? So if I give you 2 tensors, T and S, so let's say T is an n by n by n tensor, and S is an m by m by m tensor, then the tensor product T times S is going to be of dimensions nm by nm by nm, and just define it this way. So this is the natural analog to like matrix tensor products. And tensor power is just taking this to many times. And again, the important observation about matrix multiplication that made Strassen's observation work is that if I take a basic matrix multiplication tensor, let's say of size m, small m, and I raise this to a power d, it's exactly the same as multiplying m to the d by m to the d by m to the d matrices. So it's a m to the d size matrix multiplication tensor. And also the tensor that we get for cap set is also, you start from a base tensor of size 3 by 3 by 3, and you raise it to a high tensor power. So naturally, in these types of applications, the tensors that we care about are not some generic tensors. You start from a very simple base tensor, and you raise this to a high power, and you ask, what can you tell me about this high power of the tensor? Okay. So here's just, again, a simple observation. So if I give you two tensors, and I take the tensor product, this is going to be submultiplicative. I mean, that's going to be a simple claim. Let me just show you the proof. It's simple, but we're going to see that when we're going to try to generalize the rank, this is not going to be, not longer will be true, but some weaker versions sometimes are true. But let me just show you the proof, just sort of to make sure that we're all on the same page with respect to definitions here. Right? If T and S are rank 1 tensors, let's say T factors as AI, BJ, CK, and S factors as A prime, B prime, C prime, then just directly you compute the tensor product and you see it factors. So there's nothing deep, just check the definition here. And of course, because if now T is not rank 1, but there's some of a few rank 1 tensors, and S is not rank 1, but some of a few rank 1 tensors, then this just multilinearly extends. So just, I don't think it's worthwhile to just go through details here. Just it's simple. No, for the notion of rank is very simple. It is subadditive, it is submultiplicative. Okay? And now I want to tell you about something that I think is a very interesting conjecture made by Strassen that says the following. It says, well, we believe that there should be a way of multiplying matrices in essentially optimal time. Which said, well, that the rank of this matrix multiplication tensor should be essentially optimal, order of m squared, maybe slightly more here. But what Strassen conjectured is this is not just something that holds for matrix multiplication. This should hold for any tensor which is a high tensor power of some base tensor. And this is called this asymptotic rank conjecture of Strassen. So let me tell you about this conjecture because I don't know how many people know of it, and I think it's a really nice conjecture. So what is asymptotic rank? So I take a tensor T, some base tensor, maybe size 2 by 2 by 2 or something small. I raise this to a high tensor power. I compute the rank, then I take a dth root. And this is well defined because we said rank is submultiplicative, so it converges to a number. And first of all, let me just do one more. So first of all, just computing this is a hard problem because even if you think about T as being the matrix multiplication of size 2 by 2 by 2, if you could compute this asymptotic rank, you would figure out how hard it is to multiply matrices in general. So we believe this should be a hard computational problem. Could even be undecidable. Similar problems turn out sometimes to be undecidable, but this one I don't think it's known. But what Strassen conjectured is if you start with any n by n by n tensor, and you take its very, very high tensor power, the asymptotic rank is at most n. It's never more than n. And trivially, rank could go up to n squared. So this is much less than trivial. In particular, if you prove this for the specific 2 by 2 by 2 tensor of multiplying 2 by 2 matrices, this would prove that you can multiply matrices in optimal time. And if not, it's going to prove you cannot. So it's a hard problem. Yes?
You said that the trivial boundary is what?
N. Oh, I'll get to it in a second. Okay. Actually, so this is sort of maybe answering your question. So if I take an arbitrary, not even a tensor power, like some arbitrary n by n by n tensor, and ask what's the rank of it, the rank is at most n squared. It's a three-dimensional, yeah.
So in the previous slide, you were supposed to have a 2, right? Or you had a 4.
Oh, maybe. You're saying here, this should be... No, it's 2. Because 2 by 2 matrix multiplication is a tensor of size 4 by 4 by 4.
Oh.
Yes. Good. Thanks. Yeah. Okay. So if I give you an arbitrary tensor of size n by n by n, then just trivially it's ranked at most n squared. And if you take a random tensor, then it's not hard to prove it's going to be about n squared, up to some constants. But interestingly, we don't know how to explicitly construct tensors whose rank is even much more than n. So not even n squared. So the best bounds we know are going to be linear in n. And that's interesting because even Strassen, and there was this sort of follow-up work by Ran Raz, showing that if you could construct tensors of rank much more than linear explicitly, this would give us ways of proving circuit complexity lower bounds, which you all know are sort of famously hard problems to do. This would give us arithmetic circuit lower bounds. So what the best that we know? The best that we know is an explicit construction with this sort of constant 3.52. So the first construction was by this Chudnovsky, and then there were several different constructions, but there's one that's actually very simple that I want to show you. It's in this work of Bushundi al. And here's a tensor that has like the maximal rank that we know of so far. So you choose some large finite field, let's say fq to the n. You treat x, y, and z instead of as matrices, but as a matrices that correspond to multiplying by a constant in this large field. So right, you can view multiplication by an element of fq to the n as a linear operation on the vector space fq to the n. You compute a trace of it. It turns out this is going to have rank 3.5 to n, and that's the best that we know so far. And there are several other constructions, more complicated, giving you the same bounds. So even beating this would be interesting. We don't know even how to beat this. I mean, people can make conjectures about tensors that have higher rank. We just don't know how to prove it, any of it. But I think that's also an interesting question. Yeah. Coming from a calculation. It's a log of something. Yeah. Yeah.
This thing here is into a finite field.
Yes.
The previous one you talked about seems to be over any field.
Yes. So if you walk over, let's say, the reals, and you put in numbers that could be, algebraically independent or something, then you can prove the rank is large. But you want something where it's, then the elements are like small bit complex, like maybe small integers or something that's easy to compute. And then we don't have any better, as far as I know, we don't have any better constructions, even over, reals or complex numbers. Again, unless you cheat and put algebraically independent numbers or something like that. Okay, any more questions on that? So again, my goal is to show you how these questions come up in different areas. Okay, so now I want to move to the next notion of rank that's called slice rank. Okay, that's going to be a more modern notion of rank. So again, the starting point is the same as rank. We're going to say that the slice rank of a tensor is R, where R is minimum, where I can decompose my tensor as a sum of basic elements. But now I'm going to call these basic elements slice rank 1 tensor. So what is a slice rank 1 tensor? So again, it's easiest to define if you think about t, x, y, z as a multilinear polynomial. So we'll say it's slice rank 1 if I can decompose it as, a linear function in one of the 3 variable sets, and then bilinear in the other 2. And you have 3 options, which one you separate. Okay, that's called slice rank 1. So now we're allowing for more things to be called basic, rank 1 objects. And this is what it means combinatorially. And it's, again, a very simple observation that slice rank is less than rank, at most rank, because a rank 1 tensor is also a slice rank 1 tensor, but not the other way around. So we're just adding for more things to be called basic objects. And again, for the same reason, this is sub-additive. And again, for slice rank, for rank, the best we could prove, it's always going to be at most n squared. Slice rank, the naive bound is at most n. And again, the reason is just because, this is the trivial way of decomposing a tensor. So n is trivial, but unlike rank, here we actually have explicit constructions of tensors achieving maximal slice rank, and even a very simple construction. If you take what's called the identity tensor, and I'll show you this in a few slides, it's going to have maximal slice rank. So this is very different than rank. In rank, the maximal rank is n squared, but we don't know any construction between linear. Here, the trivial bound is n, and it's actually very easy to come up with, optimal object with maximal notion of rank. So, interesting distinction. So how did this notion come up? So it actually came up in the study of this cap set problem. Let me just remind you of the problem. So we're in F3 to the D. A line here is just 3 distinct points that sum to 0. A subset of F3 to the D without a line is called a cap set. And then we define the cap set tensor just to correspond to it. So it's going to have entries I, J, K, where we index them as elements in F3 to the D. And we put a 1 or a 0. It's 1 if they sum to 0 and 0 if not. So I want to show you how this tensor captures this Ramsey problem of asking what's the largest subset of F3 to the D without a line. So this is a tensor. And let's say A is a cap set. So it's a set with no non-trivial solution. So a trivial solution would be I equals J equals K, right? Then it sums to 0, obviously. So anything where they're not all the same, oh, what happened? Oh, yeah, okay. Okay, good. Okay, so a non-trivial is just when they're not all the same, so they have to be distinct in this case. So here's the underlying observation. If you take this tensor and you restrict to a subtensor of the indices I, J, and K only coming from the set A, then that's going to be an identity tensor. So it's going to be 1 on the main diagonal if I equals J equals K, and it's going to be 0 everywhere else. Why? Because this is what exactly our assumption about the set A. A does not contain any non-trivial solutions. So this diagonal corresponds to the trivial solutions, and all the rest are non-trivial solutions, so they don't exist. Okay? So this came up in this work. So it started from a work of Krut-Lev-Pach and then of Ellenberg and Gischwitz from about 6 years ago that sort of proved exponential bounds on the set of the largest cap sets. I mean, actually, Krut-Lev and Pach proved it in a slightly different setting first, and then, like a couple of weeks later, Ellenberg and Gischwitz sort of independently showed that their techniques could be generalized to this cap set problem. And how did they prove it? Well, I wanted to know how they proved it. I wanted to know how Terry Tao rephrased the proof using this notion of slice rank. I think it's a more natural way of understanding it. So really, this proof has 2 steps. First step is generic. It says, well, identity tensors, the ones that have 1 to diagonal and 0 everywhere else, have maximal slice rank. They're as hard as you can be in this notion of slice rank. And I'll show you the proof of that in the next couple of slides. It's actually a nice lemma. And then they analyze this specific tensor in a very ad hoc way, show that its slice rank is less than maximal. They found like an efficient way of decomposing these sort of 3-dimensional tensors as a lower slice rank tensor. So again, step 1 is very generic. Step 2 is sort of very ad hoc to this specific tensor. And I'll talk more about these ad hoc questions later in the talk because we don't have many sort of, let's say, structured ways of proving these things. Like the only ways we know to do it are very ad hoc to specific problems, and they fail for many, many other problems that we care about. So it would be nice to find some more systematic ways of doing these things. But if you put these 2 things together, automatically you get at the largest cap set of this size because that's the largest identity subtensor. So it cannot be bigger because it has, slice rank is big, but the total slice rank is small. Or maybe, and if you take a tensor and you remove a few rows and columns and so on, slice rank can never increase, only decrease, like matrix rank. So I want to show at least the proof of step 1 here because it's generic and I think it's interesting. Okay, so let's take this identity tensor. So again, very explicitly, it's the following, multilinear polynomial. You have x, y, and z, each of n variables, and the polynomial is the sum of xi, y, zi, and this sort of lemma of Terry Tao that says the slice rank is maximal. It has to be n. It's at most n, but it cannot be less than n. So what's the proof? I think it's a nice proof. So let's say the slice rank of this tensor is some number of r. Well, by definition of slice rank, you can factor this as the sum of r slice rank 1 objects. Slice rank 1 could come, you either isolate the x variables, or the y variables, or the v variables, right? One of the 3. So we have 3 parts here. This part corresponding to separating, we have a linear function of x times a bilinear function of y and z. And here for the y, and here for the z. And R1 and R2, R3 are some 3 numbers that sum up to r. So this is just using the definition of what is a slice rank. What does it mean? And now we're going to use some linear algebra. So I'm claiming that there exist subspaces, V1, V2, V3, and F to the n, that if I take this tensor, T, and I restrict it to inputs X only come from V1, inputs Y only come from V2, and inputs Z only come from V3, it's going to be identically 0. And why is this true? Because you just take V1, Fi's are some linear functions. So V1 is everything orthogonal to them. And V2 is everything orthogonal to the G's, and V3 is everything orthogonal to the H's. So the dimension of each Vi is n minus Ri. Okay, so we're going to get something interesting. The next step is to say, well, take V1. V1 is a subspace of some dimension, n minus R1. It must contain a vector whose support is at least as large as the dimension. So that's like a simple exercise in linear algebra. And let's think about the matrix where you just fix X to be V. Okay? So now I went from a tensor problem to a matrix problem, so it's easier. So what can I say about M? M is diagonal on the support of V, right? Think about just plug in here Vi. So if Vi is non-zero, you just get the diagonal tensor. So its rank is at least the dimension of V1. On the other hand, again, here's a nice sort of simple claim. If I give you a matrix and I tell you it's identically 0 in the product of V2 and V3, then its rank cannot be super big. As long as once the dimension of V2 plus V3 is more than n, the dimension of this matrix, the rank cannot be maximal. And again, it's like a simple exercise. You put the things together, you get a bound on the R1 plus R2 plus R3. Okay, so you basically reduce the question about tensors to a question about matrices that we all know how to solve. Good. So that's nice. So identity is maximum. Again, it doesn't have to be identity. Just put it in any non-zero coefficients here would work the same way. I mean, the fact that it's a 1 and not doesn't make a difference. Okay, what about how does slice rank behaves under tensor products? Is it also going to be multiplicative? And the answer is no, it's not multiplicative. Because here's an example. Take this T and this S, where they're both slice rank 1 objects, but with respect to different variables. Maybe T is with respect to the variable set X, and S is with respect to the variable set Y. You take a tensor product, it shouldn't have any nice structure. So it could have very large slice rank. So there's no reason why slice rank would behave in any way nice when you take products, tensor products. But surprisingly, it still behaves nicely, but just not when you take 2 products, but when you take many products. So that's actually a very surprising result. So before I give the technical details, I'll just say it maybe more informally. If a tensor T has less than maximal slice rank, so less than the maximal size n, if it's an n by n by n tensor, if it's less than n, and now you take a high tensor power of it. So the result is that this slice rank is going to be exponentially smaller than the trivial bound. And concretely, it's the following theorem by Blasiak and a bunch of other co-authors. And here's technically what they proved. T, let's say T is an n by n by n tensor. And let's say the slice rank of T is even 1 less than maximal, n minus 1. And now compute a huge tensor power of it, T to the tensor power of D. So you can think of n as a constant and think of D as very big. So what they proved is that that's going to be at most C to the D, where C is a constant that depends on n, and it's less than n. And if you work out the math, you get something like n minus 1 over n. So even the bounds are not so bad. So yeah, that's a very surprising fact, right? It's not multiplicative in any way, but it's about this weak notion of submultiplicativity, which is still good enough for all these Ramsey applications. So that's great. By the way they proved it, they didn't prove it directly, they proved it through studying some notion of stability of tensors. So again, I think it's a very interesting connection that they discovered.
But is it a construction?
Is it what?
Is it a construction?
I mean, is this constructive? Yes, it's constructive. You actually find this sort of... The only way we know how to prove upper bounds on slice rank is to find decompositions. We don't have any other way. Well, maybe that's another way, but I mean, this is constructive. Okay, good. Maybe before I do that, any questions about slice rank before I move to the next notion called partition rank? So again, rank is sub-additive, sub-multiplicative, very nice. But we don't know of any explicit constructions of higher rank matrices or tensors. Slice rank, also simply, relatively, still sub-additively, not multiplicative, but this weak notion. And here we do know of explicit constructions getting like the maximal slice rank.
Can you say a word about this notion of stability?
Maybe at the end. Yeah. I mean, you can prove this directly. I think the easiest way to prove it is to not talk about stability and just talk about, you can prove it directly. But the intuition came from these other questions.
In 4 dimensions, you allow it to break into 2 and 3.
That's exactly what I want to talk about now. So this notion of partition rank comes up when we say, well, that's nice in 3 dimensions. What happens into like 4 dimensions, right? So let's say, again, we have this tensor in 4 dimensions. What is in more than 3? So partition rank is exactly the natural thing you're saying, right? If I have 4 things, I can decompose that maybe x, y versus zw, right? Any 2 sets. While slice rank in 4 dimension still only allows 1 versus 3. So it's a very natural question. So this is called partition rank. And you can ask all the questions that we had before, right? First of all, it's at most slice rank, because the slice rank 1 is also partition rank 1, but not the other way around. So what do we know about this partition rank? It's still sub-additive for the obvious reasons. Okay. What's going on? Okay. What? It's a prank, exactly. It's a prank. Yes. Identity is still maximal, even partition rank. So this was proved by Naslan, and the proof is actually less simple than the one I showed. It's still combinatorial and nice, but it's more delicate. N. So if you look in, so for example, now can even use a board. So if I give you, for example, the n by n by n by n identity tensor, then its partition rank is n. And even if you have to break into groups of not just one versus the rest, it doesn't help you. There's no non-trivial way of decomposing it. And you can ask, is this also, it's not going to be submultiplicative for the same reasons, but maybe it's going to be weakly submultiplicatively, like we saw for slice rank. And unfortunately, so initially we were hoping the answer is yes, but unfortunately the answer is no. So there exists a 4 tensor, like an n by n by n by n tensor, that its partition rank is basically as small as it can be, 2. I mean, if it's 1, everything is trivial, it's 2. But if you take high tensor powers of it, it basically becomes as bad as it can be. So it's not even weakly submultiplicatively. So this has to be proved with Lysakov and Zuidam. And the construction is simple. So I'll show you the construction at least. So it's a very natural construction. So you take x, y, z, w to vectors in f to the n. And I'm going to break x into 2 parts, the first half and the second half, and y and z and w. And you just get this sort of polynomial. So it's obviously partition rank 2, because each part here is no. You break into 2 parts, and of course we have to break into 2 versus 2, because it was 1 versus 3. We know that's not going to be true. So you do the natural thing, and it turns out you can prove that its partition rank is essentially maximal if it is large enough.
So this is what?
This is what?
The blue diagram in how should we read it? T of x, y, z, w.
So you take the inner product. Inner product, yeah. Yes. Inner product. Thank you. Yeah.
And how do we prove no bounds of time?
Okay, good. So I'll tell you. So the only way how to prove it is to show that it contains essentially a maximal identity, tensor inside it. So it turns out, so you can use techniques from, additive combinatorics to show this contains basically, you can find inside it essentially maximal identity tensors. Okay. Okay, so unfortunately, partition rank doesn't satisfy this weak submultiplicative list, so somehow, hopefully it satisfies something, but we don't know what. So now let me move to even another notion called analytic rank. And that's going to be sort of different than all the other notions of rank we saw so far. So all the ones we've seen so far started with saying there's going to be a base object called rank 1 object, and we're going to decompose our tensor as a sum of those. Analytic rank is going to be defined so very, very differently. So it actually came up in higher order Fourier analysis, that I know some people here study, and it's not going to be this type of combinatorial rank. And I think if you've never seen this, the definition is very weird. So I want to first illustrate this using matrices, show you why it's at least natural there, and then extend this to tensors. So let's say we work with matrices. So matrices just correspond to bilinear forms. So let's fix some finite field, FQ. So this definition only makes sense over finite fields, and it's the most natural over prime finite fields. So let's say Q is prime, and choose some complex root of unity omega of order Q. And let's take the following bilinear form corresponding to the identity R by R matrix. So whatever notion of rank we come up with, this should have rank R, right? So it's rank R, but let's do it in a very weird way. First, let's compute what's called the bias of it. So the bias is going to be the following thing. We're going to choose X and Y random elements in FQ to the R. We're going to take omega, this root of unity, raise it to this power of t, and compute the average. So we take this average of powers of roots of unities. And actually, an interesting observation is, this is not going to be a complex number. It's actually going to be a number between 0 and 1, a real number. And the reason is the following. Fix X, and think of this as now a linear form on Y. There are going to be two cases. This linear form could be identically 0, and then that's just going to be 1. Or that's going to be not an identically 0 linear form, in which case the average is going to be exactly 0, because the average of powers of roots of unities. So this is exactly the same as just a probability over X. If we plug in X here, this linear form in Y is identically 0. So it's some number between 0 and 1. And for this specific linear form, the only case where I can do it is if all the X's happen to be 0. Right? That's going to be Q to the minus R. So how do I translate Q to the minus R back to R? We'll just take minus log of base Q of this number. Because, why not? So we get R. So at least for matrices, this gives us the same number. But now we can try to do the same exercise for tensors. So again, now let's say T is going to be like a 3-dimensional tensor. We can again compute the bias. So in exactly the same way. Now it's going to be the probability of choosing X and Y randomly that the linear form in Z is identically 0. And we just take again the same thing before, minus log of base Q of this bias. And we're going to call this the analytic rank of this tensor. So again, the reason this came up is because this turns out to be an interesting object of study when you're doing high order Fourier analysis. But what I want to tell you about today is how this gets connected to all these other notions of rank we saw today. Yeah. This depends on Q, yes. So this depends on Q. But also rank depends on Q, right? If I give you a matrix, an integer matrix, over different fields, it's going to have different rank.
Yeah, but in ways that are not so obvious.
What's that?
I mean, how it depends on Q is far from being clear.
Yes. Yes, I agree. This depends on Q. Yes. So one thing that's sort of maybe is a bit surprising, this is also sub-additive, even though it's not defined as a sum of rank 1 objects. But it's still sub-additive. So here's the one corollary you could get from this statement, that it is at most a partition rank. Why? Here's a proof. Let's start with partition rank 1 objects, T. If it's partition rank 1, then by definition it factors as a product of, let's say, T prime on some set of the variables and T double prime on the rest. And what's the bias of this tensor? Again, this is just a definition of the bias, and we thought this is a probability that if I fix all the variables except one, it's going to be identically 0, which in particular is at least a probability if I fix T prime, I'm going to get identically 0. T prime is a multilinear polynomial, and you can sort of, it's not hard to prove that any multilinear polynomial, the most likely value it gets is 0. So it's at least 1 over q. You take log q of that, you get 1. And now, because analytic rank is subadditive, if I give you a tensor T with partition rank R, just write as the sum of R partition rank 1 tensors. For each one of those, we just verify the analytic rank is at most 1, and because it's subadditive, the analytic rank is also at most R. Okay? So we have this so far this chain of inequalities that say that, well, we have the rank here. This was at most the slice rank, which is at most the partition rank, which are all combinatorial. And now we have this analytic rank, which is an analytic notion of rank. And also here, it's easy to prove that identity is essentially maximal. Yes?
Maximal here is not n, right?
It's only, so identity will give some constant times n, but you can find a different tensor to give you maximal. But now it won't be identity.
Okay.
Actually, here, if you take the multiply and I think field elements is going to give you the maximal. I think that here, let's say for 3 tensors, if I take trace of x, y, z, where I think of x, y, z as elements in f q to the n, that's going to have the maximal analytic rank. And identity is going to be the same up to some constant. So it's almost maximal. Okay. So we saw this. What about the other direction? So it turns out the other direction was heavily explored in Howard de Fourier before we even invented the names analytic rank and partition rank. So if you look at the literature, it's called, the term is like bias implies low rank because, analytic rank is like log of a bias and partition rank is what we call low rank for polynomials. And the first results were that if the tensor has some constant analytic rank, then its partition rank is also going to be constant. But the bounds were like super, really, really horrible, like worse than Ackermann type bounds. Really bad. And then there was this sort of really, really, I think, impressive result about 3 years ago that showed that actually you can reduce these sort of Ackermann crazy things into polynomial bounds. So this is all by Jenser and by Milicevic. They are independent works that discovered the same thing at the same time. In between there was a lot of intermediate works that was skipping, but for the sake of time, let me just tell you about that. And then also even more recently, so some people here and also, Cohen and Moshkovitz show that in some cases you can even reduce polynomial to linear bounds. So linear is what we believe the answer should be. That's like the natural conjecture to make here. And Tami and David and Arim and also, so Cohen and Moshkovitz showed that in some cases we can actually prove it, not in the full cases, but again, there's no reason to believe that with some more work you can improve the things to show that linear is the right answer always. Okay, so that's very, very interesting. And the proofs are also very technical, so they're not as simple as they use a lot of algebra and combinatorics and a lot of really interesting ideas. Okay, now let me go to even another notion of rank called geometric rank. And these notions come up by saying, like Nati was saying, this analytic rank seems to really depend on the field. What happens if you want to work over infinite fields? Or when you don't want to care about the field, what can you say then? So we said analytic rank is defined naturally over finite fields, and it doesn't extend naturally to infinite fields, because how can you define this over infinite fields? Okay, let me just say this. Okay, so here's one way you can do it. You can ask, let's say I take a tensor T, defined over the integers. And now let P be a prime number going to infinity. Let Tp be the evaluation of this tensor modulo P. Compute the analytic rank and take the lim inf of it. What do you get? Well, a priori, there's no reason you get some nice answer. But turns out you get a very, very nice answer. You get an answer that moves us from, combinatorics and analysis into algebraic geometry. Turns out the number that you get that was called geometric rank in this work of Koparty, Moshkovitz, and Zudam is really the following thing. So you show the following variety. So you take all the x and y's, where, the tensor on x and y is identically 0. You take this over the algebraic closure of the field, and you ask what is a codimension of this variety. So now we have this algebraic geometric notion that happens to coincide as a limit of this analytic rank when the field becomes big enough. And since there were, I just checked yesterday, there were maybe 4 or 5 other papers exploring this notion of geometric rank, and I think there's many, many possibilities here. How to maybe use this, and even the work of, I told you about in the previous slide, of linear, okay, no, even before. Okay. Sorry. Okay, so at least this work here of Cohen and Moshkovitz really comes from trying to use this notion of geometric rank to get to the optimal bounds for analytic rank. But there's still some caveats in the technical stuff.
So which Moshkovitz?
Which this one? This one? Sorry.
Which Moshkovitz?
Oh, which Moshkovitz? Guy Moshkovitz. Yes, that's a good question, right? More than one. Yes. But only one of them makes sense. For at least for this type of work. Yeah. Okay, good. So we saw, I think, 5 notions of ranks, and maybe it's a good time to start to conclude. So we saw several notions of rank. So the first one is what's called this classical notion of tensor rank. And this comes from, so the 2 applications I told you about are in algorithms, so understanding matrix multiplication and also complexity theory, arithmetic circuits. And there were these new notions of combinatorial notions of rank, slice rank and partition rank, that came up naturally as techniques to study Ramsey problems in some settings. And then there was this analytic notion that came up naturally in higher order Fourier, and then we were able to connect this both to this combinatorial notion, to partition rank, and then also to this sort of algebraic geometric notion that is sort of we still don't quite understand enough. And what was the connection? So there's this chain of inequalities here. So analytic rank is the smallest, and partition rank we know these 2 things. The 2 last one, we believe they should be the same up to constants. People can prove polynomial connections and even linear in some cases. And again, there's this sort of newer notion of geometric rank that is still sort of, at least I don't understand it enough. I think it's a very interesting connection. Now I want to tell you about some questions that at least are interesting to me. So first of all is how can we analyze tensor ranks of whatever notion? In particular, these notions of slice rank and partition rank were super useful for really giving strong bounds for these Ramsey problems, like CAPSET, and a few other ones. But for many, many similar problems, these techniques fail. And we have no clue why they fail. So in all these problems, you can come up with a very natural tensor, and you're trying to understand, does this tensor have high rank in whatever notion of rank you care about, or does it have low rank? Well, how can we prove a tensor have high rank if we explicitly find a very big identity tensor inside it? How do we prove it's low rank? Very ad hoc ways. We don't have systematic ways of proving any of these things. So I think the first question here is to try to come up with some systematic ways beyond just of hoping to find some decomposition by luck. Okay? That's one question. So there's one way you could hope to do that. What's the one way you could hope to do it? Well, we know that slice rank is sub-multiplicative, at least weakly. So if you can prove somehow, even by a computer search, that some very small tensor has small slice rank, then we can use this generic way of proving that these high tensor powers are sort of have less than trivial. So how do we do it? So first of all, we don't know how to compute any of these ranks. Like all the combinatorial ranks seem to be hard. Hard not just NP hard, but also hard in practice to compute. Even for very small tensors, we don't have any even heuristics how to do the things. However, analytic rank is very easy to estimate, at least empirically, right? I give you a polynomial. I ask you to compute the bias, which is the average of something over random points. You just sample a few random points, and you compute the empirical average. So even if you cannot prove anything, you can at least compute what it should be. Okay, good, but you can do it for small tensors. And we had this sort of weak sub-multiplicative property that works for rank and slice rank, but fails for partition rank and analytic rank. But the only thing we know how to compute, at least heuristically, is analytic rank. But we don't know what it's good for. So I think an interesting question here is to ask, are there other notions of rank, when we have 5, why not have 6 or 7 or 8 notions of rank, where maybe we can both, at least empirically, compute these things for small tensors, but also, if they're non-trivial in some way, they tell us something interesting about high tensor powers of these tensors. So I think there's a lot of room for exploration here. The third question is about constructing tensors. So I will tell you about this question. That for the simplest notion of rank, the trivial bound is n squared, but the best we want to construct is like this 3.5 to n. And again, I think this is one of the things we do a lot in, when we try to prove lower bounds, is just come up with examples that we can actually analyze. And I think the examples we know of are very, very simple, and there's no reason why there shouldn't be like more elaborate examples that are more complicated, but we can prove better bounds. And again, this is in comparison with this other notion like slice or partition rank, where we basically know the maximal objects. They're very simple. They're also analytic rank, where we know. And the last question, I just want to again remind you of this, I think, really amazing conjecture of Strassen, this asymptotic rank conjecture, that says that take any tensor whatsoever, if you take a high enough tensor power of it, it becomes simple. And in particular, the question I'm interested in is asking, let's say we knew that matrix multiplication is nice. Maybe this is true for the matrix multiplication tensor. Can we use this to prove this true for any tensor? In some sense, is matrix multiplication complete for any high tensor power? So this will be very interesting to understand. Or maybe a different tensor, either some complete tensor here. It's enough to understand it's one tensor, and we understand all of them. Okay. So this is it. Thank you. Any notions of? Reductions. There are some notions of reductions you could do, like for example, this Strassen's conjecture, you can show it's enough to put it for like 0-1 tensors. But nothing to, anyway. There are some notions, but they're very basic. Or reduce one to the other? Yeah. So one natural way is to say that you take a tensor, you apply some linear map on the coordinates, you get a different tensor. So that's one notion. That's like the most common notion of a reduction you can do here. Like taking a subtensor is a special case of that. But that's it basically. Yeah.
Because Nati did not ask Nati's question, I will ask it. What is stability of that?
I don't want to define it. It's something technical that they define so that they can prove what they want to prove. So it's not a natural. To me, it's not a very natural property. It's something that it's more technical. I mean, they call this stability. I'm not sure why it's called stability, but no.
Because there is some stability of rank for matrices.
No, there are many notions of stability in many different areas. And this is also called stability. And I'm sure they had a reason why it's called stability, which I don't know. But, yeah.
If you merge this with the tensor powers, if you merge it with symmetry or antisymmetry properties, like considering symmetric tensors and antisymmetric tensors, since in the theory of differential forms we use antisymmetry, we use powers of differential forms to get stuff about ranks, maybe something.
Maybe, yeah. I mean, the reason I want to talk about this here because I'm sure people coming from different fields have different tools, and maybe using different set of tools would be a good thing to study these things. Because we already have combinatorics and linear algebra and now algebraic geometry, so why not more tools? Yeah, I think makes perfect sense to me. Maybe if you assume some symmetry about the matrices, you can prove something. In particular, a lot of the techniques people use to study, matrix multiplication and in general algebraic computation involve understanding symmetry. So, it makes sense. Yeah.
Are there also applications of slice rank and related things to the real field or infinite fields? Problems revolve
possibly. I think this Ramsey questions are more naturally stated over finite fields, and if you take the obvious extensions to the reals, and these things don't work anymore. Yeah, I mean, I don't know of some, but maybe there are. Yeah. I mean, there's no reason not to define them over there. Yeah, but again, you need an application in mind to do it.